would like to thank and acknowledge our sponsors, Voice Astro and Chroma Technology. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer service, including free technical and application support, and they remain committed to serving both the scientific and technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served includes fluorescence microscopy, flow cytometry, biomedical instrumentation, surgical devices, machine vision, multispectral imaging, and of course, everyone's favorite, astronomy. All right, and now it's time to introduce today's instructor. A software engineer by trade, he graduated from MIT with a degree in mathematics. Since then, he's worked on communication systems, parallel processing computers, and he even spent 9 years at the Harvard Smithsonian Center for Astrophysics working on the data system for the Chandra X-ray Observatory. An active member of the AAVSO, he served on the council for 2 years and continues to serve our community today as the head of the Photoelectric Photometry Observing Section. Today, he's here with us to teach us all about photometric transformations, one of the most important and yet least understood facets of advanced photometry. To many people, myself included, transformations can seem like black magic. Fortunately for us, we're about to hear from a true expert on the topic. So settle in, get ready to take notes, and please welcome your instructor, Tom Calderwood. Welcome, Mr. Calderwood.
Let's see, how are we doing here with the screen? Everyone see that, I hope?
Yes, it does have your toolbar on the side, though.
Well, can't do anything about that.
Okay.
It's a little, that's strange. That didn't happen before, but it's happening now. There always has to be some minor anomaly in these Zoom presentations. Well, good morning, afternoon, and evening, everyone. Today we'll discuss photometric transforms, an important topic that is not widely understood. My goal here is to give you a general overview without getting too bogged down in the details. I'm sure you've heard of the Johnson system. This is a standard that astronomers use to put their photometry on a common scale. Transformation is how your own data get mapped to the standard. I'd like to start with a rough analogy from audio electronics. When a compact disc of music is being mixed, the engineer tries to make the recording sound just like the live performance. The sound is evaluated on high-fidelity reference speakers. However, when I bring the compact disc home, I play it on my own stereo, for which the speakers are not that great. My speakers are a little bit weak in the treble and very weak in the bass. But my amplifier has controls that let me compensate for the defects in my speakers. I can boost the treble a little, and I can boost the bass a lot. This is a kind of transformation. It puts my stereo's sound back on the standard. When we come to photometry, every observer's equipment will deviate somewhat from the standards. Transformation is how we compensate for that. Here's a simplified transmission curve for a Johnson B filter. You can see that it picks up a lot of blue light, a little bit of green, and just a sliver of violet. A filter is primarily characterized by its passband, the range of wavelengths that get through. The two sides of the filter are known as the cutoffs. Now here's the rub. The Johnson filter that you bought for your camera does not exactly match Harold Johnson's own filter. Here I've shown a couple examples, one where the filter is a little bit shifted compared to Johnson, and the other where the filter is a little bit squashed. And the story gets worse. Johnson used a photomultiplier that had a very different color response from your electronic camera. And even the telescope matters. Your optics introduce a slight shift in the color balance. The important point is that Johnson magnitudes are what his instrument recorded. And that's why we need transforms. When we make a magnitude measurement, our result will be brighter or dimmer than Johnson. Transformation consists of adding a positive or negative offset to our measurement. Okay, let's talk about colors. Through an individual filter, you get magnitudes. Colors are the magnitude difference through two different filters. So some common ones are B minus V, V minus R, and R minus I. B minus V is probably the most commonly used color. And here's some B minus V colors for some familiar stars. You can see for a blue star, it is slightly negative, whereas for a red star, it's close to 2. Vega has a neutral spectrum with a B minus V of 0. Here's a simplified spectrum for an A0 star. The intensity is the same in B and V. Consider how your filter and Johnson's filter sample that spectrum. Your filter picks up extra light in V, and it loses light in U and B. But the intensity of the light that you do sample is the same as for the light that Johnson sees. You will report the same magnitude as Johnson. Okay, but now consider a K1 star, which does not have a flat spectrum. The extra light that you gather in V is more than the light you lose in U and B. You will report the magnitude brighter than Johnson. If that was hard to visualize, consider this extreme case where your filter is shifted way to the red. Clearly, you're going to be picking up brighter light than Johnson's filter saw. Now, since we practice differential photometry, the story becomes more involved. Consider the case where your variable star and your comparison are both K1. You get extra light from the target star, but you also get extra light from the comparison star. This means that the difference between the target and the comparison is unaffected by the fact that your filter has shifted. But what if the comparison is an A0 star? Your filter continues to get extra light from the target, but it gets the same amount of light for the comparison. This will throw off the differential measurement. Now, as I said, color is the difference between two magnitudes. Contrast is the difference between two colors. For BV colors, the contrast is called delta B minus V. For any of the, if the delta B minus V is positive, that means the target, the variable star, is redder than the comparison. It doesn't mean it's a red star. It simply means it has more red light. With that detail, we can now discuss the specifics of transformation. The standard magnitude equals the instrumental difference, okay? The standard differential magnitude equals the instrumental difference plus the transform. The transform consists of a product of two factors: the color contrast and epsilon, a value that depends on your instrument. Epsilon is the coefficient for a transform that is linear in delta B minus V. Each of your filters will have its own epsilon, and each epsilon is associated with a specific color. For V-band epsilon, you can base the epsilon on V minus V, V minus R, or V minus I. AAVSO has adopted a naming convention that explicitly identifies the color for a coefficient. If you've looked at some of the metadata that pops up in the new light curve generator, you may have seen these abbreviations: TVBV, TVTR. This is what they are. So how do we find epsilon? The procedure is to measure reference stars having widely different colors. And we see how much the instrumental magnitudes differ from the standards. Here we do it in V-band with a red and blue star pair. The standard magnitude difference and the color contrast are known from the catalog. We then measure the instrumental delta. If your instrument deviates from Johnson, you are either too sensitive in red or too sensitive in blue. If in red, the red star that you sample will be too bright. If in blue, the blue star will be too bright. We plot the photometry this way, with star color on the x-axis. Against the y-axis, we plot the difference between the standard magnitude of the star and our measured instrumental magnitude. Here's a simple example to consider. The red and blue stars both have magnitudes of V equals 0. When we measure the blue star, we get an instrumental magnitude of minus 1.73. Okay. The red star instrumental magnitude should be the same. It has the same V magnitude. In all likelihood, it will not be the same. If your instrument is a good match to Johnson, the two data points will lie on a flat line. A steep line indicates that your instrument is a poor match to Johnson. I won't drag you through the details of all this, but I'll just say that the slope of that line is the difference in standard magnitudes minus the difference in instrumental magnitudes, all divided by the color contrast. We can rearrange that slope formula so that the difference in standard magnitude equals the difference in instrumental magnitude plus the slope times the color contrast. That should look familiar. Epsilon is the slope of the line. Now, I've presented a simplified story here. Real filters differ from standard filters in complex ways. The linear transform is an approximation. Let's say I sample stars with a range of colors. The points might not lie on a line. In this situation here, the transform requires delta B minus V and the square of delta B minus V, each with its own epsilon. My instrument, I use a photoelectric photometer on a Schmidt-Cassegrain telescope. My response is fairly close to Johnson. And in general, you want your epsilons to be less than 0.1 in absolute value. Here's a case where a bad transform was used. Most of the data are from an observer I'll call Fred. Before the dotted line, his magnitudes were in reasonable agreement with the other observers, but afterwards they're way off. At the point of the line, he drastically changed his transform coefficient, more than tripling it. And you can see the consequences. Johnson is one of a multitude of photometric systems. Another important one is Cousins, which defines V, R, and I bands. Cousins V is identical to Johnson V. Johnson did define passbands for R and I, but they are now obsolete. Today we work with the combined Johnson-Cousins UBVRI system. And something to be aware of is that there's a lot of Johnson R and I data floating around. Most of the RI data you find in Simbad are in fact Johnson data. Here's how the pass bands for R and I compare in the two systems. As you can see, they're quite different, and consequently, you can expect quite different results. Another important system is Sloan for the Digital Sky Survey. Here I show the 5 Sloan passbands in comparison to the 5 Johnson-Cousins passbands. Now, a complication has arisen in the Sloan system. 2 sets of filters were originally made. One set went into the survey telescope. The other set went to the US Naval Observatory. It was eventually determined that the passbands of the filters in the survey telescope had shifted slightly and no longer matched the other filters. Michael Bessel was a prominent photometry researcher. In a 2005 paper, he wrote, "In some ways, it is unfortunate that the Sloan passbands were chosen to provide redshifts for galaxies rather than to isolate stellar absorption features or to match existing broadband systems." It is also unfortunate that the passbands have been altered, as this will cause uncertainty as to whether others should copy the originally specified passbands or the actual shifted passbands. Before we close, I want to touch on two more things. Filters used to be made predominantly from sandwiches of colored glass. Many modern filters are made with interference films deposited onto glass. The shapes of the cutoffs for these two kinds of filters can be very different. And here's a simplified illustration. Interference filters generally have rectangular transmission curves. It has not yet been demonstrated that they can be transformed well to the standards based on colored glass. Another point is that the term transformation gets used in two different contexts. I have been discussing transform from instrumental to standard magnitudes, but the word also gets used in converting standard magnitudes in one system to standard magnitudes in another system. Here you see the conversions from Sloan to Johnson-Cousins. These are based on statistical averages from the data of a great many stars. Any individual stars you run through these conversions will be subject to a certain amount of scatter. Also, the conversion doesn't apply for stars that are very red. And with that, I will close and be glad to take questions.
Thank you so much, Mr. Calderwood. That was very clear. So we do have a couple questions already. Our first question here came from Raymond Oltian, who had asked fairly early on about transforming Sloan filter measurements and wondered if you could comment some more on converting between Johnson-Cousins system and Sloan system versus using calibration stars that already have Sloan system magnitudes.
It's always going to be preferable if you're trying to calibrate a let's say a Sloan filter, it's always going to be preferable to calibrate it with Sloan magnitudes, magnitudes established on the Sloan system, than from converted magnitudes. However, that certainly isn't always going to be possible. If you do use converted magnitudes, you want to use a lot of them so that you smooth out the statistical variation that is inevitable in the conversion.
Okay, thank you. All right, our next question here comes from Moises Montero, who says, the AAVSO DSLR observing manual recommends using 30 to 50 stars for getting good transformation coefficients. Nevertheless, the published AAVSO standard fields sometimes contain as few as 2 stars for use in determining those coefficients. Are these fields with very few stars actually useful for transformation?
I can't speak to that directly. In the photoelectric photometry group, we use, rather than star fields, because our photometers sample only one star at a time. So we do what I illustrated. We use just a pair of stars, red and blue. And the key is that those stars have to have really reliable magnitudes.
Mhm.
I can't speak to the details of the star fields that are used for camera calibration because I never do that myself. Certainly you want as many stars as you can, but if your choice is between leaving your system uncalibrated and calibrated according to a minimal number of stars, well, you would probably go with the minimal calibration.
Right. Okay, thank you. All right, next question here comes from Divi Ruhela, who asks, what are residuals in transformations and how are they different from errors calculated in TG?
That I'll have to pass on that. I've not worked with that at all. I mean, the residuals in transformation would be a measure of how much. I mean, again, we come up with this model for transformation, and what we discussed here was a linear model. When you actually start applying that model to actual stars, and let's say you have stars with well-established standard magnitudes, when you measure them and reduce your data, you're still not going to get exactly what Johnson got. And I presume that's what they mean by the residuals in the transformation.
Mhm.
And usually I think people don't bother to try to incorporate that level of uncertainty into the uncertainty for the whole measurement.
Mhm. Okay, thank you. All right, next question here comes from Glenn Williams, who asks, does epsilon V in a common Northeast Ohio light polluted sky, so let's say average sky, will that differ when there's smoke blowing overhead from fires? Does that need to be
Okay,
updated?
you always want to be doing your transform calibrations under clear skies. Okay,
Mhm.
you don't want to try doing this when anything is marginal in the sky.
Okay.
You want your best conditions because you want the result of the calibration to be all about your instrument, not about the atmosphere above your instrument.
Mhm. Okay. And I have a question to add on to Glenn's, which is that is it still possible to do photometry when you have that kind of reddening smoke in the sky? Or do you need to do something different then?
You need to leave the cover on your telescope.
I see. Okay. All right. Next question here. We'll take one from Bradley Walter, who asks, can you discuss the added difficulty in transforming U band and U minus B?
Okay, U-band is its own wild universe. I've just tried a little bit of transformation where I tried doing a UB system, and you wind up having to use delta U minus B, delta B minus V squared, and a third term that I don't remember. U-band is just a very strange world. And I personally haven't yet got a satisfactory method of dealing with it.
Mhm. Okay, thank you.
Is clearly an example where the transform is strongly nonlinear.
Mhm. Okay, next question here comes from Alan Gilchrist, who says, I was hoping to learn how to transform my BV RCIC data into the standards. I have taken data of standard clusters, process that data through VPhote, and run the photometry through Transform Maker. So now I have coefficients, but I don't know what to do with them.
Okay. Again, I don't do camera photometry myself. This would be a question for the, let's see, not the instrumentation, maybe the instrumentation forum, but you should get onto one of the forums used by the CCD observers and ask them what it is they do. Because again, I don't operate that way.
Okay, that's a great recommendation. We do have a CCD photometry forum, Alan, that I would highly recommend. So go ask your question there. And then anyone who's subscribed to that forum will get a notification in their email. So it may look like there's not a whole lot of activity in the forum, but a lot of people will see it. Okay, next question here. This one comes from Raymond Oltian, who asks, I found some instructions on how to make my own Johnson-Cousins filters from absorption filters. These would probably have the rounded shoulders on the transmission curves. Is it possible to calibrate these homemade filters?
Yes, you would calibrate them, as any other filter. Could you read his question again?
Okay.
There's a detail I want to pick up.
He said, I found instructions on how to make my own Johnson-Cousins filters from absorption filters. These would probably...
that's good enough. There's something important to know. You cannot make a Cousins I-band filter from colored glass. You may see some websites that are selling what they call Bessel I-band filters for Cousins. Those filters may in fact reflect what Cousins was using in his filter, but Cousins was using a photomultiplier that cut off at about 900 nanometers. So a large fraction of that Bessel filter was not registered by Cousins. I haven't seen I'm just trying to think of, I've made my own R filter out of colored glass. The transformation coefficient is a little bit high, but that was just, I was using the glass that was available from Edmund Scientific. I haven't seen the formulae for B and V filters, but I'm sure that the glass out there exists and you can make them. But the calibration procedure would be the same. But you should pay attention to whether you're getting large coefficients.
Okay, thank you. That's a good answer. Okay, next question here. This one comes from Natalia Vernia, who asks, when I try to transform measurements from different instruments to the standard system, they never match. Is this a typical situation, or is this just something wrong with my workflow?
Repeat that question.
When I try to transform measurements from different instruments to the standard system, they never match. Is this typical, or is it just me?
Okay, every transformation, includes some, degree of mismatch. It is not a perfect transformation from one system to another. In the PEP group, we did an experiment where 4 of us tried following some of the same stars, and we were able with our transforms to get remarkably close agreement between our systems. So it may be a matter of the quality of the transforms that are being calculated, but you're never going to get a precise agreement between different observers. Even professionals can't get precise agreement.
Okay, thank you. That's good information. So somewhat related to that, Timothy Weaver asked about how is the error in a magnitude measurement calculated?
Okay, well that will depend on whether you're taking multiple images with your camera and averaging them together, or taking a single image and just computing what's known as a Poisson error. I can't in this talk really go into the details of how that works, but if you look in the CCD manual, I believe you will find at least a partial explanation there.
Okay, thank you. All right, so next question here comes from Thierry Midavane, who asks, no matter what our instrument, filters, detector are, do we always have to calibrate on Vega, A05 standard star, or can it be different stars?
Okay, so we don't calibrate. Vega is the reference point for really all magnitudes, but you don't use Vega itself for calibration, because I mean, first of all, it's only one star. You need a range of colors to work with. So Vega in and of itself is not used as a transform calibration target.
Okay. Okay, thank you. Next question here, this one comes from Michael Poxon. When providing sequences, do you recommend a particular filter system? At the sequence team, we are now prioritizing Sloan filter values.
I can't comment.
Okay.
I don't do any Sloan photometry. I mean, it's a matter of what is, whatever it is that people need.
Okay. All right. Next question here comes from Divi Ruhila, who asks, how often do you need to recalculate your transformations? Do you need to do it, for instance, every time that you clean the optics?
Okay, so AAVSO generally recommends that you do it once a year, or maybe twice a year. When professionals are trying to do really precise work, they do it every night. When I clean my optics, I definitely recalibrate the instrument, particularly if you're using any kind of liquid to clean the optics. If you're just using like a dust blower, just air to blow off the dust, then no, you would not need to recalibrate.
Interesting. Thank you. Okay. Next question here comes from Ari Sequeria, who asks, would you care to comment on the photometry which is done with DSLR cameras and transforming and converting that photometry? Are DSLR photometry data points reliable, comparable, and reproducible?
Okay, so I'll say that in general terms, what I've seen is that DSLR, there's considerably more scatter. If you look at the light curves, have considerably more scatter than CCD or PEP data. We should always be trying to do the best that we reasonably can. So even if DSLR data are maybe not quite as good as what's available from other systems, it's still beneficial to transform because you're getting closer to reality. Yeah. So, I would certainly encourage DSLR observers to go ahead and transform their data.
Yeah, that's great advice. Thank you. All right, next question. We had kind of an interesting one come in on Facebook from a user who is watching, who doesn't have any background knowledge on photoelectric photometry, but is quite intrigued by the sound of it. And they looked up photometers and found a device listed as a spectrophotometer for lighting, and wanted to know if that's useful, if that's the kind of photoelectric photometer you're talking about.
No. What I would suggest for this questioner is to go to our website, and we have a section that's devoted to the different observing groups, and there is a link you can follow to the Photoelectric Photometry group.
Okay, I will share that link with the questioner on Facebook, and that is great advice. If there's anyone else here who's interested in photoelectric photometry, I know that Mr. Calderwood has some excellent resources on the photoelectric photometry page. Okay, next question. This one's an interesting one from Robbie Mukherjee, who asks, I'm using a CCD and I don't have any filters yet. Can these unfiltered observations be transformed?
No. Just, not to put too fine a point on it.
Okay.
And also it should be pointed out, I mean, we talk about, each of these epsilons is associated with a color like B minus V.
Mhm.
Well, to do the transform really properly for B band, you need the data for both B and V.
Mhm.
So if you were, you would typically get transformed B and V magnitudes by sampling with both the B and V filters.
Okay. Okay, thank you. All right. Let's see. We had quite a few comments come in that I'll get to in a minute. Okay, here's another question. This one's from P. Chaudhuri, who asks, is it possible to do any meaningful photometry from an extremely light polluted inner city sky, Bortle 8 or 9? If not, what is the minimum Bortle sky required?
Okay, I can't speak to a minimum Bortle. Obviously, light pollution is a problem. What you need to do, in my opinion, is stick to the brightest stars, so that the signal, the light you're getting is strong in comparison to all the noise you're picking up from the streetlights. It's, Bortle 8 and 9, that's just really tough. I don't know of, I can't give you a list of targets that would be good in conditions that difficult.
Okay. I know simply from talking to other AAVSO observers of people doing at least wide field photometry of sorts with DSLRs and similar under inner city skies. So I know at least that is possible. If you can do more of the narrow field CCD photometry, I don't know either. But to P. Chaudhuri, I would say at least investigate DSLR photometry. You can definitely do that under your skies. Okay, next question. This one comes from Divi Ruhela, who asks, does an astrophotographer's red, green, and blue filter set transform well to photometry standards?
Generally speaking, no. They were set up for completely different purposes. You will see in the AAVSO list of filters, when you go into the light curve generator, you can say, show me the following filter bands. And I believe you will see options, for instance, for the green, red, and blue. But in general, those are not a good choice to use. Now, in the DSLR world, we're kind of stuck because we have to use the filters that are built into the camera sensor. The V filter in the camera sensor is a reasonable match to Johnson. The blue and the R are not as good. And if you have a star of relatively, a really blue star or a really red star, you can get into trouble.
Okay, thank you. Now we had quite a few comments come in from helpful viewers, I believe, during the earlier question about someone who had produced the transform coefficients but wasn't sure how to apply them to the data. So I'm going to go ahead and read out those comments. We had a comment that said you can enter those coefficients into VPhoto and use the transform applier tool to apply them to your data. So that's a good point. Thank you. Actually, we had several people second that. We also had a comment come in from Bradley Walter, who said, get a copy of the Hendon and Katchuk book, Astronomical Photometry, and that will tell you how to apply your CCD transformations. And it was written in the era of photoelectric photometry, but the methodology still applies to CCD photometry as well.
Let me just interject that yes,
Please do.
that book does go into what transformations are all about, but it's not going to give you any instructions for the mechanics of how you would do that with currently available software.
Okay.
So I think that was the questioner's real point in that inquiry.
Yes.
How to actually turn the crank, and that book will not help in that regard.
Great point. That's good to know. Okay, thank you. And then I think that was all the suggestions that came in. So we'll go on to the next question. Let's see. So Hal Heaton asks, when photometric data are reported to the AAVSO, is there any way that the AAVSO can assess the quality of the transformations used? And then maybe even filter in the future the results based on that quality? Or does the differing quality of people's transformations just result in noise in the results?
Okay. The different the different quality of transformations does result in noise in the result. Actually, the primary issue is that people aren't transforming their data at all.
Mm-hmm.
Most observers simply aren't transforming their data.
Mm-hmm.
One thing that can be done, and there's hopefully there's going to be a task force getting formed to examine data quality issues. And one of the potential benefits that could be added to our current data system is to include metadata for the value of the transform coefficient, which you can see in some observations. You'll see the TV_BV. The observer, although not required to, very helpfully provides the number.
Mm-hmm.
And so that gives you, in a sense, of one handle on whether the transform is a reliable one. In general, evaluating whether data are good or not is something that has to be done in the context of other data. You can't just look at one data point. You have to look at a bunch of data.
Mm-hmm. Okay, thank you. All right, and then we had several questions come in, all on the same topic, which is, do you have any recommendations for references, books, articles on the subject of transformation and practical photometry? Just anything you would recommend to people wanting to learn more after this webinar?
Probably what you would see in the CCD manual would be most
Mm-hmm.
helpful, since most people are working with cameras. The published descriptions, like the Hendon and Kachuk book, and also an earlier one by Hall and Genet,
Mm-hmm.
again, are from the photoelectric era, and so are not as readily interpretable in the context of cameras.
Mm-hmm.
I would look on the AAVSO website at the CCD manual and maybe the DSLR manual to get a sense for how this works.
Okay, great suggestion. Thank you.
And I believe we have some recorded webinars on how to do transformation.
Quite possibly. I don't think that we have had one recently since I started hosting, but there have been more webinars than that. So check out the YouTube channel and perhaps there's another one.
I thought that maybe Ed Wiley and Ken Menzies had done one, but maybe I'm wrong.
That's quite possible. Yeah, I would check out the archive.
If that hasn't been done, then that's a very good candidate for a future how-to webinar.
Absolutely, yes. Great suggestion. That I put the link to the page with the observing manuals on it into the Zoom chat, and I will copy paste that over to Facebook. Please feel free to check that out. That has both the CCD observing manual and the DSLR observing manual are linked on that page. Okay, next question. Here's an interesting one, comes from Bradley Walter, who asks, usually when you're creating your transformations, you're using colors from adjacent passbands like V minus V or V minus R. Is there any reason why you can't use V minus I when transforming R, since it gives a wider coverage of the R passband?
Well, V minus I makes no reference to R band.
Mhm.
You're not sampling in R. So I don't see how that would work. Again, when you're doing your actual photometry for a given band, let's say R band, you would be taking data in R, and then you would also take data in another passband.
Mhm.
Um, and your calibration would be in that same pair of passbands.
Mhm.
So, I mean, it may in fact be mathematically reasonable to do what he's suggesting, but I don't offhand recall seeing any justification.
Mhm. Okay, thanks. All right, next question here. This one comes from Moises Montero, who asks, when I get my B and V instrumental magnitudes in order to obtain the B minus V value, sometimes the B value does not reach an acceptable signal to noise ratio. But if I dial up the exposure time in order to get a good signal to noise ratio in B, that saturates the V value. Do you have any recommendations for what I should do?
Okay, this sounds like a DSLR question, because it sounds like you're getting the B and V in the same exposure.
Mhm.
If it was a filter wheel situation, you would simply increase the exposure for B and leave it the same for V.
Mhm.
Short answer is there's really not much you can do. Something that can be done, and actually is used quite a bit in the PEP group with fairly good success. If your comparison and if your variable star has a stable B minus V,
Mhm.
you can in principle use a catalog value for it, not instead of using the measured value. In my own photometry, I work in two filters, and the delta B minus V is a value that can, using the transformation coefficients, the delta B minus V, standard delta B minus V, can be recovered from the instrumental magnitudes. And that's where I get my, when I apply my transform and I need a delta B minus V, that's where I get it. But you can, in the absence of that, just use catalog B minus V values
Mhm.
for your target and comparison. And again, that's not ideal, but if the option is to not be doing transforms, then it's better.
Interesting. Thank you. Okay. Next question. Actually, we had a couple of questions which are related to extinction. So first question, should you correct your observations for extinction before you calculate or apply transformations?
Okay, so this is going to depend on how big the field of view is for your camera. Okay, with a CCD having a narrow field of view, you generally don't need to worry about extinction,
Okay.
because the stars are so close together in the sky that the difference in extinction between them is of little or no importance. If you're working with a DSLR, which has tens of degrees of range, spatial range, then it's certainly something to think about.
Mhm.
And probably the best approach in that case is to use, rather than trying to measure the extinction with the DSLR, is to just adopt a default extinction value. For instance, in V band, it's common for observers near sea level to adopt an extinction value of 0.25 magnitudes per air mass.
Hmm.
If you live in a high and dry elevation, it might be less than that. At my own location, I'm at 3,500 feet in a desert environment. I've seen my extinction go, as low as like 0.14. But certainly, if you're doing DSLR work and your target and your comparison are at substantially different elevations, then it will certainly be helpful to apply at least some correction for extinction.
Thank you. And the next question on that topic is a follow-up question from Bradley Walter, who asks, so you may not have to worry about first order extinction, but what about second order extinction?
Ah, one of my favorite topics. Okay. For those of you who haven't run into this this term, second order extinction, as you might expect, extinction values are much higher in B band than they are in R band. R band light, is just not nearly as badly affected by extinction. And of course, U band is even worse. However, for B band, what can happen is that even within the range of wavelengths passed by the filter, just by that one filter, the extinction is worse at the short wavelength end. And this is what is called second order extinction. I think very few people compensate for this. I happen to do it. And I would certainly encourage people to look into that. I don't know what resources we have. I will say this, the PEP manual does talk about second order extinction and how we calibrate for it. So that might be a useful starting point just to get your hands around the problem.
Very interesting. I'd never heard of that. Yeah, interesting. So that PEP manual, for everyone here in Zoom, that will be linked from the link which I put in the chat a few minutes ago to the observing manual page. So if you want to read some more about second order extinction, I do recommend you go check that out. Okay, and another question here on the topic of extinction. This one comes from Hal Heaton, who says, I suspect that the transform coefficients depend somewhat on the zenith distance. Do you have any guidance on the maximum air mass or zenith distance that you should use when gathering data for these transformation coefficients?
Okay, certainly, yes, there is some effect. You want your calibration targets to be as high in the sky as you can get them. And obviously, ultimately you're limited by what calibration fields are available. But given the choice between one that's low in the sky and one that's high in the sky, go for the one that's high in the sky.
Yeah, absolutely. Okay, next question here from Bill Shummy, who asks, what are the advantages of photoelectric photometry over regular camera photometry?
The primary advantage from my point of view is that it is much simpler. The equipment is easier to understand, easier to operate. It has substantial drawbacks in that it's much slower to use. And for most of us in the PEP group, the photometers we're using, we work with stars, brighter than 6th magnitude. So the photometers we happen to be using are not that sensitive. So it's kind of a niche group. We have to choose our targets carefully. But I just, I like photometers. And I also kind of like, with the photometer, you're actually out there under the stars with the telescope, flipping the levers and doing all that. And while my photometer is integrating, I like to just look up at the sky because I think it's pretty to look at, as opposed to sitting behind a computer screen inside. Again, if you're interested in the PEP group, you can contact me. I should be accessible through the web pages for the PEP group.
Wow, now I want to do photoelectric photometry.
I mean, that's what I really like about the photoelectric photometry is that it is much easier to understand.
Well, very cool. You just made a great case for it. Okay. So next question. Let's see. This one's fairly specific. It comes from Roger Venn, who asks, I'm planning to install a particular camera on my C14 telescope, which already has installed true balanced non-photometric filters in the filter wheel. Can I apply some sort of correction values to these filters in order to transform the photometry data, or do I just need to buy a whole new set of filters which are meant for photometry?
You need to buy a whole new set of filters. The only reason I would suggest trying to transform is if for the moment you absolutely can't get the filters. As you may be aware, there's been this famine in the filter supply. I don't know if it's gotten fully resolved yet or not. But in all cases, it is preferable, if not highly preferable, to use a photometric filter.
Okay, thank you. Next question here. This one comes from Thierry Midavane, who asks, what is the best photometric catalog available for comparison star magnitudes today?
Well, what is the most, what I would recommend is that you use the AAVSO variable star plotter. Which provides magnitudes for comparison stars. If I am if I am in a situation where I can't use what that is providing, then I tend to go to the General Catalog of Photometric Data, otherwise known as GCPD. But generally, unless there's some specific reason not to, use the data in the variable star plotter.
That's a great recommendation.
Which I believe is being updated to include Sloan magnitudes. So the range of passbands available in that system is growing.
That's good to know. Thank you. Okay, next question. Here's one from Raymond Oltian, who asks, are transforms, or can you transform data from CMOS sensors?
Oh, yes.
Okay, great. Good to know.
This is independent of the sensor technology. It doesn't matter, your CMOS sensors are a little bit different from CCDs, and the CCDs are very different from photomultipliers, which are in turn very different from, my photometer has a photodiode, and all this stuff can be transformed.
Okay, thank you. All right, a couple extra questions here. So one was, is transformation required for submission of data to the AAVSO?
No, it is not.
Okay. Okay, thank you. And then also, we had a question here asking, are all photometric filters unique, like every single one a little bit different from each other, or can you have a transform coefficient that applies to, say, this filter from this manufacturer, and that's close enough?
I mean, no, that doesn't work, because remember, the transform, although I talked a great deal about filters, the transform also depends on your camera and your telescope. So it's not just the filter that you're calibrating, it's the whole optical train.
Yeah.
So whatever is you're using, you have to calibrate on that system yourself.
That's a good point. Thank you. Okay, then we had a question. So this was a follow-up question from Glenn Williams, who had asked about doing transformations under smoky skies previously. Glenn says that he did calibrate epsilon V under clear skies. Does this mean that all of his measurements made when there was smoke in the sky are completely worthless?
They're suspect.
Right.
And you can, in some situations you could say, well, any measurement at all is better than nothing. but smoke in the sky is a serious problem, and it's going to degrade the value of the photometry.
Mm-hmm.
You certainly, if you were to choose to submit that data, you would definitely want to put into the comments that you had smoke in the sky.
Mm-hmm.
So that way people can evaluate. They can look at it and say, okay, this is where we understand what this is about.
Yeah. Okay. Good advice. Thank you. Okay. Next question here. So for the AAVSO, the R and I filter codes in the light curve generator, and when you're submitting data, did those mean Johnson RNI or Cousins RNI?
Let's see. I'm trying to remember what the current convention is. I believe it's Cousins.
Okay. Okay. Thank you.
And I believe there is a separate identifier for Johnson R and Johnson I. I mean, it is R lowercase j and I lowercase j, uppercase, like that.
Interesting. That's good to know. Okay, and then we also had a couple of questions about sources for the various equations. So Michael Poxon had asked about, is there some sort of one-stop shop resource out there where he can go to find out the various transformation related equations?
The short answer is no.
Mm-hmm.
And in fact, I mean, what you're going to be doing when you actually do a transform, you're going to be collecting a bunch of data and then doing a least squares fit to the data. So that, like it or not, you're going to be dependent on a software package to be, turning the actual dials and levers to make it happen. And again, in the case of PEP, where we just use 2 stars, then the math just falls. I mean, that business of this epsilon being the slope, that's just simple algebra from that diagram. So I can't, if you're wanting to understand the mathematical details of a multi-star calibration, I can't specifically speak to a source that would be, an approachable resource. I mean, what you're doing, in effect, you're getting data. In that diagram I showed, okay, I've got these 2 stars. Okay, I'm doing a fit between those 2 data points, which is always a perfect line. As you add more stars, it's no longer a perfect line. But the basic idea is the same. I think before I dig myself any deeper, I'll cut it off at that point.
Okay, thank you. Okay, and then we had a couple of comments come in. So on the topic of the last question, James DeYoung had a comment that Brian D. Warner's paper, A Practical Guide to Light Curve Photometry and Analysis, or actually it's a book, A Practical Guide to Light Curve Photometry and Analysis, published in 2016, is a good source for relevant equations. So that's one. He put the title into the chat. And then also Alan Gilchrist has commented that the software manual for the transform generator might also help. So those are 2 resources. And then also we had a comment here from Glenn Williams, who had been asking about smoke, who said that he has, just FYI, not been doing photometry on smoky sky nights so far. We'll continue to not do that. But that in order to find out which nights are significantly affected by smoke, he uses smoke maps which are published by NOAA. So that's could be a useful resource, especially for people who are living in the western half of the country.
Another thing you can do if you're, if you have a list of, top 10 targets that you're always looking at, see how many counts you're getting on the star. If they're down by 15%, something's going on in the atmosphere.
Mm-hmm. True. All right. And then also there was a question about the formulae for conversions between different magnitude systems. Do you know of any useful references for those sort of conversion formulae?
There are, but I don't know them off the top of my head.
Mm-hmm.
So I'm afraid I can't answer that.
Okay. All right, thanks anyway. And then it looks like we're down to the last couple of comments. So we had a comment come in from James DeYoung saying that one of the best standard fields for creating transformation coefficients for both CCDs and DSLRs is Landolt SA 110 using Brian Skiff's red extension stars, and that field has the largest color range of any standard field that he knows of. So I will go ahead and actually copy the name of that field into the chat here in case anyone wants to reference that.
Okay, I will add just one thing there.
Go ahead.
That when you get down to the really red stars, like B minus V of 2, those stars all vary.
Mm-hmm.
So that limits the range of your calibration. However, if you can get a field that has a bunch of those red stars and you use the averages of them all together, you may be able to extend your range deeper into the red. I just want to caution people about using single red stars in the transform calibration, because that's risky.
Okay, thank you. Good advice. Okay, and then we had a comment come in from Brian Skiff with a link to a paper for converting between the Sloan system and the Johnson-Cousins system. So I will go ahead and copy that link over to the chat so that everyone can see it. Thank you for that. Okay, and then looks like this is our last comment here. An anonymous attendee said that since DSLR cameras are taking images in red, green, and blue filters at the same time on the various pixels, you can use software like Siril, S-I-R-I-L, to separate out the three channels and then transform them. So that's good to know. Thank you. For anyone in the anyone with a DSLR in the audience, you might want to take a note of that. And oh, we just had a last minute comment come in from Brian Skiff, who says that Landolt SA 110 field is strongly reddened. So the red stars are ordinary K giants that have been reddened further and they're not variable. That's useful. Okay, thank you. And it looks like that brings us to the end of our questions and comments. So with that, I think I'll go ahead and put up the end slide and begin our closing announcements with the very most important announcement of all, which is an enormous thank you to Mr. Calderwood from all of us here at the AAVSO for an excellent and very clear presentation. Thank you. I would also like to thank again our sponsors, Boyce Astro and Chroma Technology. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer service, including free technical and application support. They remain committed to serving both the scientific and technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served includes fluorescence microscopy, flow cytometry, biomedical instrumentation, surgical devices, machine vision, multispectral imaging, and of course, astronomy.